Hello all. In the last sessions we were discussing about various combinational logic circuits. Today in this session we would be discussing two more combinational logic circuits which would be the end of the syllabus. Okay, so we have gone through various combinational logic circuits. The topics that we are going to discuss today is about magnitude comparator and code converters, the two most important combinational logic circuits. First, let's look into magnitude comparator. So basically magnitude comparator is a combinational logic circuit which is used for comparing two digital numbers. Okay, when we talk about digital numbers, I mean binary numbers. You can take 1 bit, 2 bit, 3 bit or n bit binary numbers, make comparison of that and obtain the results. Okay, so as you can see, magnitude comparator is a combination logic circuit which compares the binary numbers and find out whether the binary number is greater than, equal to or less than the other binary number. So when you look at this particular block diagram, we can see I have taken two inputs here, A and B, each of 1 bit for example, and when you look at the outputs, output would be either A greater than B, A equal to B or A less than B. Okay, so basically the comparison happens bit by bit starting from MSB to LSB bit, and at each bit position the corresponding bits of the numbers will be compared. If the bit in the first number is greater than the second number, A greater than B, B output will be activated. If both the bits are equal, A equal to B output will be activated, and if the first number is less than the second number, the third option A less than B will be activated. Okay, so once first bit is done, the similar thing is repeated for the second bit until all the bits in the given input are covered. Okay, so this is all about your magnitude comparator. If all the bits are equal, A equal to B. If the first number is greater, A greater than B. If this first number is smaller, A less than B. Okay, so we can design this magnitude comparator using AND gate, OR gates and XOR gates. Let's look into the design. This is an example of 1 bit magnitude comparator. Okay, as you can see, when I talk about 1 bit, each input has 1 bit. As you can see in the truth table here, A input is of 1 bit, B input is of 1 bit. So for 1 bit each for 2 inputs, I have 4 different combinations: 0 0, 0 1, 1 1 0 and 1 1, and the output here are represented as A greater than B, A equal to B and A less than B. When I take the first combination, it is 0 0, both A and B are equal and hence A equal to B output is high. The second combination, A is 0, B is 1, that is A less than B, hence A less than B is output activated. The third combination 1 and 0, that is A greater than B, hence this is activated, and for the last combination A is 1 and B is 1, both of them are equal and hence A equal to B will be activated. So this is the truth table for 1 bit comparator of 2 inputs. Okay, so based on this truth table, I have derived the logic expressions. For the first output, that is for A less than B, I have only one output, that is A bar B. For A less than B, I have A bar B, and for the second output A equal to B, I have two combinations, that is AB 0 0 and AB as 1 1. So I have it as A bar B bar plus AB. And we look at the third output A greater than B, I have only one output as high, that is for the input case wherein A is equal to 1 and B is equal to 0, for which I have A and B bar. So first we'll explain what is magnitude comparator, 1 bit magnitude comparator, and this is the truth table of that, followed by the logical expressions. So using that logical expression, we are going to draw the logic diagram. As you can see, I have taken 2 bits and the inversion of them, and first is A greater than B, for which A greater than B, A and B bar. So A and B bar combined together, it is A greater than B, and for A equal to B, it is A bar B bar plus AB, which is XNOR gate, and hence I have taken XNOR. Okay, don't take 2 AND gates and OR gates and complicate the circuit. Replace that with only one gate, which is XNOR gate, and then finally for A less than B, it is A bar B. So A bar and B will give you A less than B. So this is how we draw the combinational logic circuit for 1 bit magnitude comparator. Okay, similarly let's get into 2 bit magnitude comparator. Okay, so here when I talk about 2 bit, as you can see, I have same inputs A and B, but I am taking 2 bits in each of the input. So for A, I represent it as A0, A1. Similarly for B, I represent it as B0 and B1. Okay, now when I talk about this, I have 16 different combinations: 0 0 0 0 0 0 0 1, 0 0 with 1 0, 0 0 with 1 1, and then 0 1 with 0 0 combination. See, I'll take 0 0 combination in A input and take all the 4 combinations in B, 0 1 in A, all the 4 combinations in B, 1 0 in A, all the 4 combinations, 1 1 in A and all the 4 combinations. This way we will cover the combinations of all possibilities, okay. And then similarly, like what we have seen, 0 0 is 0, 0 0 is 0, both of them are equal, hence A equal to B. When I talk about this, A naught A1 are 0 and this is 1, that is A less than B. When I talk about this case, even in this case, A less than B, okay. So similarly, we go for all the combinations and generate this truth table. After we generate this truth table, we will go for truth table. See, in the previous case, we had only few inputs, like only one of the output is high in each of the output case, hence we didn't go for K-map. We have directly given the logic expression. But when you go for this, there is need for K-map because there are so many outputs high in each of the output variable, okay. So for which I have taken K-maps for A greater than B, one K-map for A greater than B, one K-map for A less than B, and one K-map for A equal to B, okay. So as you can see, for A greater than B, wherever I have ones from this particular truth table, I have just placed them, and once you are done with this, go for grouping. So here I have made a quad, and then this is one, this is left out, so this is one pair and this is another pair. So from this K-map, this is the logic expression. Similarly, when you look into this, from this K-map I have this logic expression, from that K-map I have that logic expression. So using these 3 logic expressions that we have obtained for each of the outputs, A greater than B, A equal to B and A less than B, we will draw the combinational logic circuits. As you can see here, A naught, A1 are the 2-bit inputs, 2 bits of A input, B naught, B1 are 2 bits of the second input B, okay. And here A greater than B, A equal to B and A less than B, okay. So this is the combinational logic circuit for 2-bit magnitude comparator. Next, so similar to 1-bit and 2-bit, you can design for n-bit, you can go for 4-bit comparator also, okay. So the next topic that we are discussing today is code converters, okay. So code converter is a logic circuit that changes the data represented in one type of binary code to another. Sometimes based on applications, we need to convert binary code into XS3 code, or binary code to gray code, or gray code to binary, or vice versa, okay. So in these cases, we make use of these combinational logic circuits which are called as code converters, okay. So first let's look into one type of code converters, which is 4-bit binary to gray code converter, okay. So here in the input we have binary numbers. So we have taken 4-bit binary to gray, hence I have 4-bit input B0, B1, B2, B3, all 16 combinations 0 to 15 from 0 0 0 0 to 1 1 1 1. Similarly, the output here is gray code. I want to convert the input binary into gray code. We have already seen what are gray codes, right? 1-bit representation, 1-bit variation, okay. So if suppose you have this kind of truth table, what do? We again go for K-maps. K-maps for what? G3, G2, G1, G0 separately, because we have n number of outputs high for each of the output variable, okay. So based on this truth table, here I have taken K-map for G3, G2, G1, G0, okay. So I have taken the K-maps, I have done the grouping. As you can see here in the first thing, I can go for this octet, okay. All 8 ones together I can form an octet. So this is the logic expression for that. And then this is the K-map for G2, where I can go, where I've gone for 2 quads, and then here 2 quads again, and here 2 quads again, okay. So this is the K-map simplification of the 4 outputs of the given truth table, okay. So from this logic expressions that we have obtained, we will draw the logic diagram, okay. So as you can see, G3 is directly B3, okay. The B3 input would be passed to G3 directly, hence we don't make any connection B3 to G3. And when you look at G2, it is B3 B2 plus B3 B2, okay. So this is XOR of B3 and B2, okay. So XOR of B3 and B2, similarly B2 B1 and this one, okay. So this is all about the input binary to output gray code converter, okay. Now let's look into the second conversion, the vice versa of what we have seen earlier, gray to binary, okay. So basically these are the 4 steps that you have to follow when you write it in the exam. First thing is, write the truth table showing the relation between the input and output. So here in this case, the input is gray and the output is binary. Okay. After you do that, for each binary coded output, draw the K-map, and step 3, from the K-map that you have drawn, obtain the simplified logic expression, and then using that particular thing, in step 4 we realize the combinational logic circuit of code converters using the basic logic gates that we have seen. Okay. So these are the 4 steps that you have to follow for designing the code converter circuits. Okay. Now as you can see here, we have gray code as input, binary as output. We have done the same thing. First I have put the truth table, and from the truth table you are supposed to draw the K-maps. From the K-maps generate the logic expressions. These are the K-maps for each of the inputs. Okay. So here also we have done the same thing. B3 is G3 directly, and then G2 XOR G3. For 4 cases we have drawn the K-maps. We have generated the outputs B0 and B1, and using them we have drawn the logic diagram. Okay. Not just about code converters. The 4 steps that you are supposed to follow for designing any combinational logic circuit, 5 in fact. First one, explain what is the problem statement, what is input, what is output. Second step, draw the truth table along with the block diagram. Third step, use K-maps for simplification if required. For small circuits you may not require it, based on the requirement, based on the number of outputs being high. For each case you need to go for K-maps for deriving the logic expressions. After that, from the K-map, go for grouping, derive the logic expressions, and using logic expressions you are supposed to draw the logic circuit. Okay. So this is all about that. Next code converter is binary to BCD. Okay. So same steps, we will convert 4-bit binary to 5-bit BCD words or anything. So first we will draw the truth table and find the relation between input and output. Second step, for each BCD output that we have, because BCD is output here, so for each BCD output we will draw the K-maps, and step 3 we will obtain the simplified expression for each of the output variable in the given truth table, and using the logic expressions that we have obtained from the K-maps, we will draw the logic diagrams. Okay. So these are the common steps that we follow for any combinational logic circuit, as I told you. Okay. Now this is the truth table for binary to BCD. Okay. So you have taken 4-bit binary and 5-bit BCD numbers. Okay. So for each of the inputs we have drawn the K-maps. So we have 5 outputs here, D0, D1, D2, D3 and D4. For each output we have drawn the K-maps, done the grouping and obtained the logic expressions. So as you can see, as I told you in the earlier classes, go for the maximum grouping that is possible, because when you go for maximum grouping, the term that we get will have less number, we will get less terms, and we will have very less number of logic gate being used if you do so. Okay. So as you can see here, we have done 2 quads, as here we have only 2 ones, so that is a simple pairing. So here 2 quads again, here in this case this is 1 quad and this is 1 pair, and here it is 1 octet. Okay. So based on the number of ones which are high, go for highest grouping. If that is not possible, go for the nearest lowest grouping. Okay. So this is how we generate logic expression for each of the K-maps, and using this logic expressions we draw the logic diagram. Okay. So here I have taken 4-bit binary, so B0, B1, B2, B3. Along with that I have taken inverters, and we have 5-bit BCD. So the outputs are D0, D1, D2, D3 and D4. So using these inputs we have derived the logic expressions for each of the BCD outputs. Okay. So this is the logic diagram for binary to BCD code converters. Okay. So this is all about today's session, where we have discussed about how to design combinational logic circuit for code converters and comparator. Thank you.